So today we're going to be talking about an introduction to Polygon zkEVM because this is something that just recently got launched on mainnet. So before we get into that, just a little bit about myself. My name is Manny, or Coding with Manny. I'm a developer relations engineer for Polygon Labs. If you want to see more tweets about me in terms of tutorials or breaking down like very complex concepts, definitely follow me at Twitter at Coding with Manny. But that's a little bit about myself. I've obviously been in tech for 15 years as well. So, and I'm really happy that I get to work at Polygon and work on really, bleeding edge tech when it comes to blockchain technology. So that's a little bit about myself, and let's jump into it. So the good news is that Polygon zkEVM mainnet beta is live, basically. This was announced on the 27th, so this week. So this is very, very new. The testnet had been out for a little while, but now we are full mainnet beta that's out. So you can start deploying contracts to mainnet if you have NFT projects or if you want to do some decentralized exchanges. This is a really interesting opportunity to start at the ground floor because it is essentially just starting out for people to start deploying very, very interesting dApps on Polygon zkEVM. But I'm going to go into some basic understanding of what Polygon zkEVM is and how does it work, and kind of hopefully go into the process of showing you a little bit of how that would work from a developer point of view as well. So first off, it's like, what is Polygon zkEVM? Polygon zkEVM is an L2 solution, so basically a layer 2 solution that is leading for zero knowledge proofs in terms of Ethereum scaling. And what that means is that it's an Ethereum scaling equivalent solution, or EVM equivalent solution, meaning that like if you have existing smart contracts, developer tools, and wallets, they should work seamlessly as if you were dealing with Ethereum itself. It's just a slight network change in that sense, but as far as it goes, the entire experience is as if you were dealing with Ethereum. And what's interesting about Polygon zkEVM is that it harnesses the power of basically zero knowledge proofs to be able to like reduce the number of transactions that are performed on L1, reduce the cost, and then inherit the security from L1. So, but one thing in terms of a couple caveats, right? When we hear about zero knowledge proofs, but we'll go into this, is that Ethereum is a layer 2 solution, but it is also not privacy focused. So it's not a privacy chain. It is just a way for us to be able to scale transactions, reduce the costs in a more efficient way. And it's all related to Ethereum. It doesn't relate to Polygon POS, the other chain in that sense. This is really to be able to scale Ethereum in itself. So you might be wondering why Polygon zkEVM, like where did this idea come from? So Polygon zkEVM's goal, like I mentioned, is to scale Ethereum's transactions. So its TPS, or transactions per second, reduce those costs of transactions, which is going through batching, which we'll talk about a little later on. And then also reduce the cost, or reduce the friction rather, for developers to learn something new. For some other solutions that are out there, for zkEVM solutions, you need to learn an extra step or another programming language just be able to interact with this zkEVM. In this case, if you are a Ethereum developer, you are a zkEVM developer. It's that simple. And again, leveraging the security of L1. And what that necessarily means, or leveraging the security of Ethereum, is that there's a contract that actually exists on Ethereum. And the only way to process batch transactions is to interact with that contract by posting, hey, this is my batch, and this is how I got there through a zero knowledge proof. And we'll dive into that deeper. So the first thing you might be wondering is like, what is a zero knowledge proof? Like, what is this? Zero what? So I'll go over a basic idea of zero knowledge proofs using, and I believe, forgive me if I'm wrong, but I think in Finland it's called Misha Valu in that sense, or Where's Waldo? For me, I grew up with Where's Waldo, or in French we said Où est Charlie? But I think it's pretty international with Where's Waldo in terms of this game. So to illustrate an idea of zero knowledge proofs, what I'm going to show is, what if I could prove to you that I knew where Valu or Waldo is on this without actually pointing to you or showing you how I got to that solution in that sense? And this is kind of the basic principles of zero knowledge proofs, is being able to prove something or prove a statement without actually giving any context or any additional information in that sense. So here would be like an example. Here's the graphic. I don't know where Waldo is. For time purposes, I didn't actually find Waldo, but I'm going to just point out this is the example. So here's the proof. Imagine I give you this carton basically with a hole in it, and it points to Waldo specifically on the map. Now I give you this opaque board and just with a dot in terms of where it is. Now the thing is, you don't know where I positioned it in relation to the map, right? In this sense, for this graphic, you don't know if it's in the top left, the top right. You don't necessarily know how it's positioned in relativity to this dot, this open hole, to be able to see where Waldo is in that case. And that's essentially the concept of zero knowledge proof. It's like, hey, the cardboard itself is the proof of this, to be able to show you, hey, I can actually prove to you that I know the validity or the statement of where Waldo is, but not give you any additional information. And this is a very rudimentary concept of what that looks like, but it is really just, it's a very, very efficient way to be able to say, hey, I know something. I don't have to spend hours trying to explain to you how I got there, but just being able to say, hey, I know this, just trust me. You can trust this, to be able to say, I know the solution in that sense. So zero knowledge proofs, they're cryptographic in nature. So basically what that means is that they create it's a method for generating cryptographic proofs. So to verify the authenticity, it's very secure and private. So like we mentioned, we're not divulging any information. And this is really great for the privacy sector or anything to do with authentication in terms of zero knowledge, ensuring like that privacy. So information is not divulged while still just proving a certain statement. And efficient in the sense that whenever we actually compute these proofs, it's very low cost in terms of, hey, we have servers that are generating these proofs, but are done in an efficient way that it's not like, we're not back to the days of Ethereum where we're doing proof of work, where there's a lot of GPU power that's needed to be able to generate these proofs. Now, what I will say is that if you really want to dive deeper into zero knowledge proofs and have somebody who's studied it for a long, long period of time, I would definitely recommend, there was this video by Wired that talks about 5 levels of complexity in terms of explaining zero knowledge proofs to different people, and explaining it to a degree of like, hey, from novice to expert. It's a really, really great video. I definitely recommend. And again, at the end of this presentation, I'll give you a QR code so that you can actually scan this and keep this on your phones to be able to get all the links and etc. But an application example of this would be, imagine if you could log into a system, right? Prove that you're a human being, you're not a robot or a malicious actor in that sense. And then, but with generating a zero knowledge proof. Now, if we took the cardboard analogy, like we saw, where this pinned hole, we're just giving the cardboard with the pin hole in that sense. We're not giving the actual information, nothing of that. So if a bad actor or a malicious actor was able to capture that information, the only thing they would have is the proof, but they have no other information, which is to say, basically, there's no context. There's no, hey, how did you get here? What information is about this user? And this is what you can use zero knowledge proofs for, from a privacy perspective, to be able to basically prove something about yourself from an authentication point of view without divulging that information. And there's a lot of other applications with this, but at the same time, this is just to understanding the fundamental of the technology of zero knowledge proofs, and what we can use it for. Now, that said, just to recap, a zero knowledge proof is to prove you know something without revealing any additional information. So just keep that in mind, like just proving something without revealing any other information. Now, to wrap your head around this, sometimes it's a little bit hard, but I do recommend, if you have a chance, go check out that original video from Wired, and they'll definitely go into different layers of complexity to be able to explain it. Okay. So in this sense, in regards to zkEVM or zero knowledge Ethereum virtual machine, in that sense, it's a network that takes advantage of zero knowledge proofs through a technology called zero knowledge rollups, basically. And what that means is you can also use the technology for zero knowledge proofs to be able to prove that an execution was done. So the way that we do that here is that we are actually able to prove the validity of a statement. And basically what happens is zkEVM takes a whole bunch of transactions that would normally be processed on Ethereum, but through zkEVM, batch those transactions and process the execution, and then roll them up into a single transaction, right? And batch them up and post the minimal summary of that data to the Ethereum mainnet. So you can kind of see here, if we're interacting with it, we have a whole bunch of API calls that goes to the synchronizer. It says, hey, how do I kind of order these things, get them into the sequencer to say, hey, this is how I should order the specific transactions. the transactions are essentially sent over to the aggregator. The aggregator says, okay, this is a batch, but the sequencer also posts to Ethereum saying, hey, I've ordered these transactions and I've posted to Ethereum and saying, this is the batch of transactions that I want to execute. From there, the aggregator takes that and says, okay, I'm going to take all these transactions, execute them, and get their results. And then from there, create a cryptographic proof in the terms of a zero-knowledge rollup, and then post that to Ethereum to say, hey, this is how I got there. So it's like a two-step process in the sense that, hey, there's a batch incoming, and here's the state and how I got to it. And this is really using zero-knowledge proofs to be able to just prove, hey, trust me, this is the result of these executions, and here's a zero-knowledge proof to show how I got there. So basically, it's using zero-knowledge proof to roll up or capture a whole bunch of transactions and batch them up in one with one zero-knowledge proof to be able to prove these multiple transactions as opposed to individually in that sense and post it to Ethereum. So just to recap how that looks like, we have multiple transactions that are submitted to an RPC node, right? They batch these multiple transactions, and then the validity of that transaction, like we talked about, that summary of data is posted on Ethereum as a single transaction, right? And if you took the definition of finality, and this differs from person to person, as in like, hey, when is it actually considered final, and you can't actually change it. If you want from the traditional sense that where you trust Ethereum to be that final sense of Ethereum, you're saying that once the transactions is actually complete on Ethereum, that's the sense of finality. But the nice thing is, you can almost assume that as soon as you post a transaction through zkEVM to the sequencer, or just zkEVM in general, you could assume that transaction is just going to be included and assume that finality is there. But really, the idea behind it is just trying to batch transactions in an efficient way and post the result on Ethereum and how it got there. So leveraging that contract that's on L1 as a security mechanism in that sense. So the benefits, obviously, it's secure in the sense that we're just leveraging Ethereum in that sense to be able to use that contract. It's scalable. So we're looking at like, hey, we can actually batch a whole bunch of transactions off chain, execute them. And then the cost is significantly cheaper because we're not having to deal with the gas directly on Ethereum. It's almost like everybody's contributing to this one single transaction that's significantly cheaper. So we're able to do multiple transactions at astronomically reduced cost in that sense. And then the last aspect in terms of a benefit is equivalent. And this is what I talked to at the beginning, which is the idea that, hey, as a developer, how should I jump through some extra steps just to be able to interact with this network in that sense? And the answer is that you don't need to. You use Solidity. If you're able to post a Solidity contract to Ethereum, you could post it to zkEVM. It's very, very simple. It's as simple as that, but you get to take advantage of all the reduction in costs, the batch transactions in terms of the number of throughput, all the benefits that come with it, and then the idea, and still leverage the security of Ethereum in that sense. So this is just to kind of compare it. There is some other rollup solutions that exist, and one of them is called optimistic rollups. So if you're dealing with zkEVM, usually the process to be able to finally withdraw your funds through a bridge service is about the time period of about 30 minutes. Now, if you did within a traditional optimistic rollup in that sense to be able to batch these transactions, the time to be able to actually withdraw is about 7 days, which is significantly different, like significantly longer for a transaction. Now, there is other ways that optimistic rollups are working to be able to circumvent this by kind of, hey, I'll give you some of the money up front through a different transaction. So yeah, I'm able to be more liquid in that sense and speed up the process. But as you can imagine, that adds an additional cost to things, right? Where in zkEVM, you can assume that once the transaction goes through and you want to bridge it back and forth, it's really in 30 minutes, you can assume that you should have your funds either on Ethereum or in zkEVM. So industry use cases, like where we can see, like, I'm really excited about this because really, if you can think about it, it makes blockchain technology more mainstream and leveraging something that the reputation of Ethereum to be able to process these transactions. So some definite use cases are DeFi. So imagine processing like hundreds of thousands of different transactions more efficiently with reduced costs. It essentially makes DeFi projects more more profitable in that sense, because you're not having to rely on Ethereum or be at the whim of Ethereum in terms of how bogged down the network might be. Gaming is a great example of this too. And I do realize that Polygon POS is a great solution as well, but leveraging Ethereum natively for transactions is great for gaming, because it gets to the point where the transactions are cheap enough. If you can think about it, we are getting to the days where it would be negligible for game developers to say, hey, I will front the cost of having these transactions if it's like 0.0001 cent for transactions. So it makes it the idea that if you had gaming and on-chain transactions for gaming for NFT items or even a native token, it makes it more viable for gaming in that sense as well. And traditional finance is great in terms of security, because if you think about it, you want, as a banking service or any traditional finance service, you want to be able to trust the security, right? And in this sense, we're leveraging Ethereum security, which is definitely top notch in terms of it's proven test of time for a long period of time. And we're basically using cryptographic proofs to be able to prove these transactions and execute them then, but post a summary of those execution on Ethereum. So it's a great way for traditional finance to get into this. Obviously for energy infrastructure as well, like if you're trying to keep information in terms of IoT services, that would be interesting to be able to make it more viable for some of these projects to come to fruition. Because if you're thinking about it, and every time you have to post data to Ethereum, and if it's costing you $5 per transaction, it doesn't seem pretty viable. And for zkEVM, that just lets the transaction be astronomically cheaper and definitely more viable. And there's obviously like supply chain and healthcare. But one thing I will say, because there sometimes is a confusion, and I said this at the very beginning, and just to reiterate this, is that healthcare would be a solution, but most people will ask, well, is zkEVM privacy focused? And I want to just reemphasize that it is not privacy focused. So from a sense of like trying to make it HIPAA compliant or any type of compliance in that sense, you will still have to rely on some of your own cryptography or encryption to be able to, before posting it in that sense. And I won't advise that I'm like an expert in this, but you just know that the information that you will post is public. But it's just the goal of zkEVM is really for the throughput and reduction of cost, right? So how do I deploy to zkEVM? So hopefully we're going to walk through a demo, but basically the idea is that you have to, in order to interact with the network on zkEVM, you have to bridge tokens to it. And the nice thing is that you actually just bridge Ethereum or native ETH basically back and forth between Polygon zkEVM and Ethereum. The nice thing is that once you do that, you process your transactions, you can bridge it back and you get whatever minus the gas cost of doing those transactions back in terms of native ETH. And that's nice because you don't have to deal with, if you're dealing with another side chain or another chain in that sense where their token's value is somewhat different in that perspective, you have to deal with, I'm going to wrap the token. I got to figure out what the exchange rate is to be able to kind of exchange it over. In this case, you don't have to deal with any of that. It's really, you have your ETH, you bridge it over, you have that native ETH in Polygon zkEVM to process transactions. When you bridge it back, it's one for one. You don't have to deal with any exchange rates or losing any gas in terms of the transactions in terms of conversions. So that's what we're going to demo, is how you would actually bridge this from Ethereum to zkEVM in that sense. So the main way to be able to do this is, I definitely recommend, if you haven't looked at this, go to wallet.polygon.technology. So this is the wallet service, which has the bridge in it to be able to bridge back and forth. So we're going to do a demo of what that looks like. So hopefully the internet and everything works for this demo. But as far as it goes, we're going to use Gurley, which is testnet Ethereum, and then be able to bridge it to zkEVM testnet. So this is what it looks like. I'm here on wallet.polygon.technology. I've clicked over to the zkEVM new section that's been released. I'm on testnet specifically because I want to be able to bridge Gurley testnet to zkEVM testnet. So here I'm going to go to the bridging service. It's going to ask me to connect my wallet. And I'll see the prompt that should show up. Sorry, one second. There we go. I should be connected. From here, you should see that there is a bridging solution that's right in the middle where we can bridge Gurley back to zkEVM. And for this instance, I'm just going to bridge 0.05 Gurley, or in this sense, it could be Ethereum, to zkEVM. What I'm going to do is just go bridge. It's going to switch the networks to, obviously I was on zkEVM, so I'll switch over to Gurley. Confirm. And it's going to process the transaction. Now, the one thing to note, once this come up, it'll show a message to say that this will take up to 30 minutes to do the bridging. So just be conscious of that. But as far as it goes, once that's done, you're able to easily bridge it back. Now, the nice thing is that I already had some transactions already set up. So here, I'm going to claim the transaction. This is from, let's go from, I believe I have claim from Gurley to zkEVM. So this is the second process. So all I need to do is switch over to zkEVM network, the testnet. I'm going to go back to my bridge. Just refresh this just to see if it picked up the network. So I should be able to claim that basically on zkEVM testnet. So I'm going to claim this transaction. So, oh, sorry, it's not that one. It is, refresh it one more time. So deposit from Gurley to zkEVM. And this is zkEVM to Gurley. Oh, it looks like I already went through the entire process for one of them. But the idea is that you can bridge it over in terms of just the process. And what you do is you just claim it on the other side. And the nice thing is that you can actually bridge it back. And this was an example from zkEVM to Gurley. So here I'm going to make sure that I'm on Gurley in that sense. So I've processed all my transactions. And then I'm just going to claim it here on Gurley to be able to withdraw that money, or that ETH essentially, on zkEVM testnet. Give it a second. So I'll confirm that transaction. And remember, this is like the bridge service is actually locking it up. So this is now on Ethereum to make sure that it's unlocked and to have that specific Gurley ETH within my wallet. This can take a couple seconds because it depends on the RPC service, but let's give it just a couple seconds. It should have completed. There we go. And we should see that Gurley, essentially, I was able to claim that Gurley from zkEVM to Gurley in terms of testnet. Now, the interesting thing, and I will say about the bridging, is that people think, oh, well, I can bridge, great, I can bridge Gurley to zkEVM or ETH to zkEVM in that sense. But you can also bridge custom tokens. And I think I have it here under zkEVM testnet. So this is a ERC20 token. I pasted it in the contract. I can paste it here. And I can bridge back also ERC20 tokens back and forth like custom tokens. Now, the one thing to note is with this is that the bridge solution is a clone of whatever a standard ERC20 token is. So if you have custom functionality, that will be lost. So be conscious of that. But you can bridge over native tokens easily through this bridging service too. And that's essentially what I did for this 200 zkTST token to be able to bridge from zkEVM to Gurley and able to basically bridge that back and forth with native assets. So not only Gurley, but also tokens. And there is in a future release, we're trying to do also NFTs, which would be easy to be able to bridge them back and forth. And the nice thing about this, as you can imagine, more when you're bridging them over and you're processing transactions with those solutions like ERC20, or for that matter, 721, when you're doing trades, is that the gas transactions are a lot cheaper. So it's almost like saying, hey, instead of processing them on Ethereum, I can go process them multiple times, maybe divvy out like 100 different types of tokens. And then if the wallet holder wants to be able to bridge it back in terms of Ethereum, that's up to them, but you're able to process those transactions and do airdrops a lot faster and cheaper. So that's the bridging service. So the next thing I want to do, and just to kind of reiterate, is that you can actually look at the documentation for bridging, and there's a diagram as well within there to be able to show you how that bridging service actually works if you're really, really curious. So definitely check out wiki.polygon.technology. The last thing I will do is I'll demonstrate, now that I have zkEVM tokens, I'm going to deploy it to zkEVM testnet with my token. So here I have I'm on Remix, and basically I created a ERC20 token, and you can kind of see here that it's my ERC20 Tampere token. And what I'm going to do here is I've already compiled it. And then what I'm going to do is it's by the injected provider from my MetaMask. So in this case, I'm just going to make sure that I'm set to zkEVM. And then from here, I'm just going to go deploy. It'll compile it. Let's give it a second. We'll see that pending transaction, and it was complete. And the nice thing now is that Polygon Scan or Etherscan has now adopted testnet zkEVM and zkEVM mainnet natively, so you can see your contracts on Polygon Scan, and we can see the contract there already deployed. Let's wait for it. And with the number of tokens, so let's just copy this. And if I go to my assets and let's import this specific token, my ZKT, you should see that 10,000 tokens were an ERC20 token that was deployed to zkEVM testnet. And that is how simple it is to be able to just interact with it, showing you that you can use Solidity, deploy it like if you were deploying to Ethereum. And then from there, as you can imagine, like I showed before, you can bridge this back and forth. It was deployed on zkEVM, and now I could bridge it over to Ethereum in that sense too. That is it. And the last thing is, like, if you have any additional, these are some additional guides in terms of things that you could do in terms of ERC20 tokens to using Brownie or deploying NFTs. Definitely check out one of my blogs, codingwithmanny.medium. And if you do want to see this entire presentation, feel free to scan this QR code. I'll also be sharing it with the team to be able to make sure that you guys have all the resources you need to be able to go over this and really digest it in that sense. So that's it.
Amazing. Thank you.